Are you willing to trade the environment and human lives for millions of tons of cheap steel every year? Because that is exactly how the world recycles ships through a massive yet highly controversial industry. Every year, thousands of oil tankers, container ships, and giant cruise vessels are dragged straight onto beaches, where they are cut apart piece by piece using oxy-fuel torches, often with little real safety protection. From inch-thick steel plates to massive engine systems, everything is gradually broken down and transformed into raw material for construction, manufacturing, and secondary markets around the world. In this video, 5.0 Industry takes you deep inside that journey to reveal what truly happens behind one of the most controversial steel recovery systems on Earth. A typical commercial cargo ship or luxury cruise liner has an operational lifespan of around 25 to 30 years. Beyond that point, relentless saltwater corrosion, metal fatigue, and the rising cost of maintaining complex engines turn these floating assets from profitable machines into serious financial liabilities. And the pressure to retire ships can arrive even sooner than expected. During the global pandemic, the cruise industry alone lost billions of dollars in an extremely short period. That financial shock pushed many companies to retire high-value vessels years ahead of schedule, including mega cruise ships once worth hundreds of millions of dollars. Instead of carrying passengers or cargo, those ships were suddenly redirected toward dismantling yards. This constant flow of retired vessels feeds a global recycling economy worth hundreds of millions of dollars each year. More than 90% of this labor-intensive dismantling happens along the coasts of India, Bangladesh, Pakistan, and Turkey. The process begins with geography. Not just any shoreline can be used for shipbreaking. Operators look for gently sloping mudflats, low coastal gradients, and large tidal ranges that can rise and fall dramatically during each cycle. Places such as Along in India and Chattogram in Bangladesh became major global hubs, largely because nature had already shaped the perfect conditions for beaching enormous ships. Then timing becomes everything. The most critical moment is dictated by the lunar cycle. During spring tides, when the moon and sun align in a way that raises water levels to their peak, a massive vessel is driven toward shore under full power. These ships can exceed 1,000 feet in length and weigh anywhere from 60,000 to over 100,000 tons. Yet, at the right tide, with the correct angle and speed, they can be pushed straight onto land. This is not random impact. It is a calculated maneuver based on inertia, seabed depth, hull shape, and tidal timing. As the ship surges forward, its broad bottom acts like a giant steel plow, carving into the soft mud. Then, as the tide recedes over the next few hours, buoyant support quickly disappears. The vessel's immense weight settles onto the mudflat and locks the ship into place without relying on sophisticated docking infrastructure. Once the vessel is fully beached and its bow rests firmly on the shoreline, crews begin stabilizing it immediately. Heavy steel cables are attached to structural points such as the bow and major support members. These cables are connected to winches or pulling systems designed to manage huge forces while keeping the ship from shifting unexpectedly with the tide. Even a small imbalance matters. A vessel of this size does not need to move far to create danger. Just a few inches of unwanted shift can alter loads, twist sections out of line, or make cutting operations far more dangerous. To help resist movement, workers also reinforce onshore anchor points by driving steel stakes deep into compacted layers of mud. The result is a crude but effective stabilizing system that prepares the ship for dismantling. Before any cutting can begin, the vessel must be stripped of flammable liquids. Fuel, lubricants, residual oil, and bilge water are removed using high-capacity pumping systems connected to the ship's internal piping network. Thousands of gallons can be extracted from deep tanks and transferred into shore-based containment units. This step is essential. The reason is simple. Once cutting starts, temperatures from oxy-fuel torches can soar above 5,000 degrees Fahrenheit. In those conditions, even a small concentration of fuel vapor trapped in a confined space can ignite and cause a devastating explosion. After liquids are removed, attention turns to the internal storage tanks themselves. Workers attach chains and lifting equipment to reinforced points, then cut the tanks free from surrounding piping and support structures. Because these tanks can weigh several tons, movement must be carefully controlled to prevent them from rotating, falling, or striking nearby workers during removal. And the danger does not end once the tanks are out. Storage tanks are never considered safe just because they have been disconnected. Many still contain thick sludge residues loaded with hydrocarbons, heavy metals, and toxic contamination. That residue can continue releasing flammable gases long after the visible liquid is gone. So each tank is opened, drained, and tested with gas detection equipment. Only after it reaches a verified gas-free condition can it move on for further cutting and processing. With the ship cleared of major flammable hazards, crews begin the first heavy dismantling cuts. The bow section and upper deck are often cut in parallel because controlling structural balance is critical. At the bow, workers follow the ship's internal steel frame system, usually spaced at regular intervals. These frames are major load-bearing elements that define the hull's strength and shape. Aligning cuts with this hidden structural grid helps massive sections separate in predictable ways. If done correctly, giant steel portions weighing tens of tons can be guided apart without violent breakage. But this is also where risk multiplies. Corrosion, deformation, and unknown internal damage may have changed how loads are distributed over decades of service. A cut line that looks safe from the outside can trigger an early collapse if the internal forces no longer behave as expected. Meanwhile, on the deck, superstructures and upper layers are removed gradually to reduce weight over the increasingly hollow hull beneath. Workers usually cut from the outer edges inward, staying away from expected fall paths wherever possible. Near the end of a cut, they often leave a final connection point intact until cables are ready to guide the section down onto the beach. That moment is one of the most dangerous in the entire yard. A separated deck block can weigh up to thousands of metric tons. Once freed, it may not simply drop where expected. On oil-soaked mud, a steel mass can slide, rotate, twist, or collapse unpredictably. If control is lost, it can crush equipment, destroy access paths, or kill anyone in its path within seconds. And the environment itself makes everything worse. Shipbreaking yards often operate directly on mudflats mixed with oil residue, rust scale, and industrial contamination accumulated over many years. The surface underfoot can be slippery, unstable, and uneven. Workers may stand on soft mud while handling hot steel, heavy cables, falling sparks, and unstable loads at the same time. Then there is the air. Cutting through painted steel, insulation, and coated surfaces can release fumes containing lead, zinc, and other harmful compounds. Heat builds up fast. Ventilation is poor. Visibility is limited. And without strong safety systems, respiratory exposure becomes a daily part of the job. It is this combination of massive structural forces, toxic exposure, unstable ground, and unpredictable collapse behavior that makes shipbreaking one of the most dangerous industries in the world. Yet through repetition, local experience, and tightly coordinated teamwork, crews still dismantle these vessels with remarkable speed and scale. Once major exterior structures such as the deck and bow are removed, dismantling moves deeper into the ship's interior. Here the work becomes slower, denser, and in many ways more dangerous. The vessel is no longer a strong, intact structure. Every removed section changes the way loads travel through what remains. Workers cut along main beams and frames, but confined spaces make access difficult. Bulkheads, the steel walls that divide compartments, are opened one by one to create movement routes for people and materials. Instead of tearing everything apart at once, crews divide the hull into smaller blocks and remove them in a calculated sequence designed to reduce the risk of progressive collapse. As each block nears separation, cables or winches help guide it onto the beach rather than allowing it to fall freely. At this stage, dismantling is no longer just demolition. It also becomes an exercise in recovery and sorting. Large, thick steel plates are especially valuable. If they remain intact, they can be sold for direct reuse or processed more efficiently than small mixed scrap. Smaller pieces are cut down further for easier transport. The more organized the material flow, the higher the value extracted from the ship. Valuable components are also salvaged wherever possible. Copper wiring is pulled from electrical systems. Pumps, valves, motors, generators, and mechanical assemblies are removed from their mountings. Some are stripped for material value, others are repaired and sold into reuse markets. Non-ferrous metals, such as copper and specialty alloys, are particularly important because they often bring much higher returns than ordinary steel scrap. And it is not only heavy industrial parts that find a second life. Doors, lighting fixtures, furniture, steel panels, railings, electrical cabinets, and other usable items are often transported to second-hand markets near the yards. There, materials from dead ships re-enter daily life in workshops, homes, factories, and small businesses. For many surrounding communities, these markets are not a side effect of shipbreaking. They are a major economic extension of it. Still, as crews move deeper into the ship, conditions become harsher. Enclosed spaces trap smoke and heat. Fresh-cut steel remains red-hot. Footing gets worse. Escape routes narrow. Every removed plate changes the shape and behavior of the remaining structure. That is why dismantling a large vessel cannot be finished quickly. Depending on the ship's size and complexity, a yard may need dozens or even more than 100 workers operating for 2 to 3 months to reduce one vessel into transportable material. Once the ship has been broken into large sections, the next stage is size reduction. Massive steel blocks are cut further into smaller pieces suitable for handling, trucking, and furnace charging. At this point, the objective is no longer to separate ship structure, but to prepare steel for the next industrial step. Large sections are cut into pieces only a few feet across. This work is still done gradually, line by line, so crews can control separation and avoid sudden movement. Oversized steel is a problem for recycling plants because very large blocks do not melt evenly. Smaller, more consistent pieces improve furnace efficiency and reduce energy waste during remelting. Even here, risk remains high. Pieces that are no longer part of a ship are still heavy enough to injure or kill if they slip, flip, or roll unexpectedly. Cables, hooks, magnets, and basic machinery are used to drag, lift, and stack the steel on the same muddy ground where dismantling began. After leaving the yard, the recovered steel travels by trucks or barges to scrapyards. There, it enters a very different stage of its life. Now the metal is no longer treated as part of a vessel. It becomes ferrous scrap, reusable steel feedstock for new industrial production. Scrapyards collect material not only from ships, but also from demolished buildings, old machinery, vehicles, containers, and household metal waste. In these stockpiles, the boundaries between industries disappear. Ocean steel and land steel become part of the same recycling stream. Before the scrap enters a steel plant, it must be inspected. Loads are checked for size, coatings, oils, plastics, and other contaminants. This matters because the quality of incoming scrap affects melting efficiency, emissions, and final steel composition. Better sorting means better steel making. From there, the material is consolidated and prepared for furnace charging, often into electric arc furnaces that can operate with very high scrap content. In other words, the ship's journey does not end on the beach. The beach is only the point where the vessel loses its identity. And this is where the story changes. A ship that once crossed oceans carrying cargo, passengers, fuel, or machinery does not simply vanish when workers cut it apart. Its disappearance is physical, but its material survives. The hull becomes beams, bars, coils, plates, and wire. Engine parts become workshop equipment. Interior fittings become second-hand goods. Copper moves into new motors. Steel returns to foundries and re-enters city skylines, factories, bridges, warehouses, and homes. What makes shipbreaking so disturbing is also what makes it economically irresistible. It is violent, dangerous, dirty, and deeply efficient. It extracts value from what would otherwise be stranded capital. It turns obsolete vessels into raw resources at enormous scale. But that efficiency comes with visible costs: environmental contamination, worker risk, and a dismantling model built around some of the harshest labor conditions in modern heavy industry. That contradiction sits at the center of the entire business. On one side, shipbreaking helps recover vast quantities of steel without mining new ore. It supplies affordable materials to developing economies and creates jobs across dismantling yards, resale markets, transport chains, and recycling plants. On the other side, the process often shifts the true cost onto coastal ecosystems and vulnerable workers who face the heat, fumes, unstable structures, and toxic residue directly. So when a giant ship reaches the end of its service life, the real question is not whether it will be recycled, it is how, under what conditions, at what human cost, and for whose benefit. Because the image most people see is simple: an old vessel dragged ashore and cut into pieces. But the reality is much bigger than that. It is a global system where finance, steel demand, labor, geography, tides, engineering, and survival all collide on a strip of muddy coastline. Every cut in the hull is connected to another industry somewhere else. Every removed plate is part of a supply chain. Every salvaged part extends the life of material that once traveled the world at sea. In the end, shipbreaking is not just the death of a vessel. It is the moment an ocean machine is broken apart so completely that it can re-enter the world in 100 new forms. And that may be the most unsettling part of all. The ship disappears, but almost nothing is truly lost. If you want to explore more industrial journeys where giant machines vanish only to be transformed into something new, follow 5.0 Industry.